Hello and welcome. In this tutorial, you will learn about XLDs in MVTec HALCON. XLDs, or Extended Line Descriptions, are data structures typically used for precise machine vision tasks, like edge detection and measurements. Unlike regions, they are sub-pixel precise. XLDs include contours, polygons, and parallels. A contour is a sequence of sub-pixel accurate 2D points. Typically, the distance between these points is about 1 pixel. The points are connected by lines. The level of detail and resolution of polygons are usually much lower. Parallels are used rather infrequently, and contours are the most common, so that's what we will focus on in this video. To begin, it's important to know that XLD contours contain attributes. On the one hand, there are local attributes, like the angle or the widths at all contour points. On the other hand, there are global attributes that describe XLDs as a whole. For example, a global attribute can be an approximate classification as a line segment, elliptic arc, or circular arc. Let's have a look at an example in HDevelop. In this image, we want to detect this line and check its width. To detect lines, lines Gauss is a commonly used operator. Since its parametrization is not trivial, we provide a helper procedure with more accessible parameters. Here we give the maximum line width and the typical contrast of the desired contour. Thus, we can detect the line quite easily. Next, we want to visualize the width of the extracted line. With getContourAttrib XLD, we can query the width to the left and the right of the contour at every coordinate. For the visualization, we additionally need the angle for all coordinates. Speaking of coordinates, we can query those with getContourXLD. With a little bit of trigonometry, we can then calculate the coordinates of the left and right border. With GenContourPolygonXLD, we can generate a contour from row column coordinates. The visualized result looks like this. As you can see, the contour is detected well. Now, you might, for example, want to find out which parts of the line are thicker than a certain threshold. Thus, we find all indices where the width is greater than 6 pixels. Using these indices, we generate crosses at the respective coordinates. Let's have a look at another example to introduce additional functionalities. In this noisy image, we want to get more information about this circular sector. First, with Edges subpix, we can extract relevant edges. Because of the noise, the edges are interrupted at random points. To fix this, we can use Union Adjacent Contours XLD. HALCON offers a variety of union operators for more sophisticated use cases as well. Next, we segment the contours into lines and circles. This also adds a global attribute representing the approximate type. Then, we filter out these smaller contours. Finally, we want to determine which contour represents the outer edge of the circular sector. To do this, we loop through the contours and query the global attribute cont_approx. If it is 1, that's the contour we're looking for. To get more information about this circular sector, we can fit a circle to it. The circle fit gives us the center coordinates, radius, and the start and end. Using this information, we can generate XLDs representing the circular sector and the full circle. Lastly, we can, of course, convert XLDs into regions, and vice versa. This concludes this tutorial. We hope this gave you some insights on how to work with XLDs in MVTec HALCON. For much more information, have a look at the operator reference and the numerous HDevelop examples we provide. Thank you for watching.